All right, everyone. So I'm going to be talking about Green's functions solutions to Poisson's equation. That's section 5.2 of Franklin. But if you're not reading Franklin, that could also still be helpful. Right. So it starts off by talking about the uniqueness theorem, which just says that there's some unique solution to Poisson's equation, which is the Laplacian of phi is equal to like 4 pi rho. And essentially, what we're able to say from this is that if phi is like set to be some like function, or if the normal derivative of phi is, so this is like with the normal to the volume, is given to be some function, then and this has to be true on like every part of the surface, then there's a unique solution to Poisson's equation. Okay. And so because of this, we can say that we can sort of think about two different boundary conditions, where you could have one boundary condition where we're setting phi equal to some function, or we could have another boundary condition where we're setting the normal of phi equal to some function. And really quickly, the normal of phi is, like, I'm just writing it as sort of shorthand for the normal dotted with the gradient of phi. And these two things are identical. Okay, so I guess this would be equal to g as well, right? So what we're able to say is that there's two possible boundary conditions that we can think about then, and those boundary conditions would be if we're setting phi equal to some function, and this is called a Dirichlet boundary condition, or we could have it where we're setting the normal derivative equal to some function, and this is called a Neumann boundary condition. All right. And so when we have Dirichlet boundary conditions, we know the specific value of phi, which means that in this part of the surface integral, we know the value of phi, which means that we can solve this integral theoretically if we can find the gradient of g. But when we're setting like phi equal to some function, we don't know specifically this. Like, we don't know this specifically. So we can't really solve that part of the integral. So we actually want to eliminate it. And how we eliminate it is literally just by setting g of r prime at the surface equal to 0. So in order to handle Dirichlet boundary conditions, we set g of r prime at the surface equal to 0. Okay. And then with Neumann boundary conditions, we have the opposite is true, where we know what the gradient or the derivative of phi is, but we don't know what phi is specifically itself. So what we instead want to do is we want to eliminate the left side. We want to eliminate this term. And how we do that is by setting the gradient evaluated at the surface equal to 0. Okay. And so then we have that essentially partial g over partial n is equal to 0. Or I guess evaluated at the surface specifically. Because if we think about having some volume, we're not going to say that like g at this point is equal to 0. Like, we don't know that's true. Like, it's generally is not true. But what we do want to say is we want to say that on the surface, or sorry, actually, this applies to both. Yeah, what we want to say is on the surface, g is equal to 0. Or this is like specifically for Dirichlet boundary conditions, but for Neumann, you would be saying like here would be the gradient of g, or the gradient of g on the surface has to equal 0. And generally, this does not equal 0. Okay, and so just keep in mind, generally, those are the two types of boundary conditions that we're dealing with. And when we apply the boundary conditions, meaning like when we plug in for g or for the normal derivative of g, depending on what boundary conditions we have, we can eliminate part of this surface integral, and then we can solve the problem. All right. So what we can now think about is what happens. Or I guess before we get into the next part, we should probably think about, just to reiterate, that applying the boundary conditions to this equation at the top is going to give us a unique Green's function solution of Poisson's equation. So because we're using the uniqueness theorem when we're thinking about how phi is defined, or the normal derivative of phi is defined, we're saying that applying these Green's function boundary conditions is going to give us a unique solution. Okay? And so really quickly, the textbook talks about homogeneous and inhomogeneous boundary conditions, but doesn't ever, I don't think it really defines what that means, or at least I didn't know what it meant when I first read it. So what it says is that the Green's function satisfies the homogeneous boundary condition corresponding to the inhomogeneous boundary condition satisfied by the potential. So really quickly, if we just say the potential is equal to some function, then we know we said that we're going to set G equal G, I guess G evaluate at the surface. I don't know. I'm just going to write G equal to 0. Okay, and then if we said that the normal derivative of phi is equal to some function, we're going to set the normal derivative of G equal to 0. Okay? Evaluate at the surface. I think it's evaluated at the surface. Don't quote me on that. But so this, when you set something equal to something else, and that something else is non-zero. So when you set something equal to a function, this is inhomogeneous. Inhomogeneous, right? But when you set something equal to 0, this is homogeneous. So we can apply the same logic here. This is like in, and this is homogeneous. I guess, yeah. And so all this is really saying is that, or all the textbook's saying when it says that the Green's function satisfies the homogeneous boundary condition corresponding to the inhomogeneous boundary condition, it's just saying that we're given some inhomogeneous boundary condition, meaning that either the potential or the normal derivative of the potential is set equal to some function, and then we just make the Green's function equal to 0 because that's homogeneous. Remember, homogeneous is 0, non-homogeneous or inhomogeneous just means that it's equal to some function or a constant, because a constant is a function as well. All right, so I found that part really confusing when I was reading the textbook, but maybe some of you are a little more locked in than me. But the next thing we're going to do is just think about sort of an example where just a very standard electrostatics problem where the potential is specified on the surface of some volume. So if we have some volume and then we specify the potential on the surface equal to, I don't know, some function, then what we have here is a Dirichlet boundary condition. Okay, so when we have Dirichlet boundary conditions, we got to remember we set G of G of R and then R prime on the surface equal to 0, which means that we can eliminate this entire term. So this entire term goes to 0 because this G term goes to 0. Okay? So then what we can do from there is we can ask ourselves, like, how can we rewrite this expression now that we've eliminated that term? So the textbook does something really weird here, but I will explain what it does. So you keep this volume integral, and this is just integrating over the volume, whatever charges are in the volume. And then it's obviously over some volume, right? But then it adds on some random surface charge integral and doesn't even mention it for some reason. But it's G of R prime, but now we're integrating over some surface charge density. So that's going to be integrating over some sigma, and then obviously we're integrating over the area now. So what is this surface charge integral? Where is this coming from? So this is coming from if we have some surface inside of our volume that has some like sigma on it. So theoretically, you can include that in this first volume integral, if you write rho, in terms of some other rho plus or not of r, but you write it in terms of, I don't know, some other like rho naught or whatever. It's not a constant though. Plus like some rho times like a delta function to eliminate one variable, and then you'll get a sigma out of that. So, but all they're doing is they're just splitting up. In the case that you have some surface charges inside of the volume, they're splitting up the rho integral into one rho integral, and then, or like, or not one, one rho integral specifically, and then possibly you could have like multiple, where this is like phi naught, or this is like sigma naught, and then this is like sigma 1. So then you would have like another sigma integral, right? But I'm not going to write all that out. Just keep in mind that you can have like multiple surface charges inside that you're integrating over as well, because they're included in the volume. Actually, I need to keep that. But so that's where that term comes from. And then you keep the 1 over 4 pi term. But you got to remember we got rid of one of the terms. So we end up with just our dA prime dotted with our phi of r prime times our gradient of g. Okay. And so this is the expression for phi that we're left with, right? So now if we know g, and then if we know g and we know the surface derivative or the normal derivative of g, then what we can do is we can calculate this phi, which is ultimately what we've been trying to calculate the whole time, right? And so the way we do that is we consider like sort of the it calls it the two defining properties of Green's functions, which are and this is specifically for Dirichlet boundary conditions, but we have that the Laplacian of the Green's function is equal to negative 4 pi delta of r minus r prime. And then we have that, and actually, I think, when I wrote the Laplacian earlier of phi, it should have been equal to negative 4 pi rho, but I think I wrote positive 4 pi rho on accident. But to keep in mind it's negative, it's not too consequential, just note that mistake. But the second defining property, I guess, that the textbook defines is that, as we remember, the Green's function on the surface is going to be equal to 0. Okay. And so using these two properties, theoretically, we can hopefully calculate the Green's function. And then from that, we would be able to calculate phi. Okay. So one of the last things I want to talk about is what the Green's function represents for Dirichlet boundary conditions. So for Dirichlet boundary conditions, the Green's function is going to be equal to phi phi specifically at r, some position r, due to a point charge located at r prime, where every surface in the problem is a grounded conductor. Okay. And I'll quickly give an example of what I mean by that. So like, let's just say we had some sheet, could be infinite or not, and then we set it equal to like 5 volts, and then I ask you to like, and then I don't know, let's say there's and then I just like ask you to find the potential at this point. Like, let's say this is the origin r. What would be true is that the Green's function at like, I don't know, let's just say like this is r prime for some reason. I don't think this is a great example because why would we want to look at this random point? But like, let's say this is r prime. The Green's function at this point in space would be, or not at this point in space. The like g of r prime would be equal to, whatever phi would be here, if this surface was actually grounded. So if we grounded this surface and then calculated phi, assuming that there's like some point charge at r prime here, then that would be the Green's function. And then, I don't know, you could theoretically plug back into this expression up here, and then boom, you would have a solution. I don't think this is a great example, but I don't know, I can't think of a better one. But regardless, we can calculate the Green's function in this manner, and then we can use that to solve phi. And so that's all I really wanted to talk about for this video, but thank you.